Honors Algebra 2, Chapter 14, Section 4, the last one we'll cover for this chapter. We're going to be solving the trig functions in this section. To solve these trig functions, it's similar to all of our other solving techniques where we want to isolate the function, the parent function. So we want to first remove all of our shifting, stretching that occurs to the parent function. So in this example here, we have sine of x is the parent function. So our first goal is to isolate that parent function, just so to remove the other things. So we want to first add the root 3 to both sides, and then we will end up dividing by 2. So we'll end up getting sine of x is equal to root 3 over 2 when we isolate the sine x. The next part is then similar to what we did in chapter 13, where we have to then find the angle measure for x that gives us a ratio of root 3 over 2, which goes back to our unit circle. And I have the sine wave drawn here to show how it also occurs on this graph, where the sine is the y value in a unit circle. So our y value here, or the sine value here, is root 3 over 2. It occurs at two different spots. And then this also occurs in a unit circle, and that's where my preference is to see it, is that the root 3 over 2 is the y value here and here of the 30, 60, 90 triangle. And so I know that this angle here is pi thirds, and then this angle here would be 2 pi thirds. So pi thirds and 2 pi thirds. Now because the interval notation right here tells us we only need the answers within one unit circle, these would be the two answers. Here's another one, cosecant. So again, isolate our function. So we need to square root both sides to isolate cosecant x. And do not forget your algebra that this would be plus or minus 2 over root 3. And then we'd want to rationalize this, but I'm not going to, because this is the cosecant function, and I would prefer to see it as the sine. So the sine of x is going to equal the reciprocal of the cosecant. So that would be plus or minus root 3 over 2. So it ends up becoming rationalized when I write it as the reciprocal function. And so I'm looking where is sine not only positive root 3 over 2, but also negative root 3 over 2. So this is similar to the last problem we just did, where our sine is root 3 over 2. So we have the pi thirds and the 2 pi thirds. But then we also have the negative. And so our y values could be negative or going downward. And so we have 4 different angles. And so the angle measures we're trying to write here are pi thirds, 2 pi thirds, same ones as the last example. I'll be this one right here. Then we also have the 4 pi thirds, and then 5 pi thirds, all the way around to this one. So this would be the 4 angles within one unit circle. And because it gives us the interval right here, that's all we need to state. Another one was sine, so I want to isolate sine x here, so I'm going to subtract 4 and then divide by 2, and I'm getting sine x equals 1/2. And then where does sine equal 1/2? So that would be these two triangles in a circle. So it would be 30 degrees, or pi 6, and 5 pi 6. So that's the two angles within one unit circle, but this problem doesn't state that we have an interval from 0 to pi. Therefore, we need to give all possible solutions, even those outside that 0 to 2 pi range. So pi 6 is one angle, but all coterminal angles also would work. So we have to add 2 pi in to state all coterminal angles. And we also have 5 pi 6 plus 2 pi n. So this is like the general form for all possible solutions for this given equation. And so the general solution is kind of a statement to help you realize you have to have that plus 2 pi n or some form of that. So for this one here, we have this problem, but notice we have sine here and sine here. So we have to use some of our older solving techniques. Since we have two terms that both have sine, we can actually factor sine x out, and we get sine squared x minus 4 equals 0. And then once we have our factors, and actually I see I can factor this again, so I can make that as sine x times, this is sine x minus 2 times sine x plus 2 as a difference of perfect squares. So I can set each of these factors equal to 0 then. So sine x equals 0, sine x would equal 2 for this one, and then sine x would equal -2. Now, for these last two, sine is always between -1 and 1, so these two are not possible. There's no solutions for those. But we do have sine x equals 0, and that on the unit circle is going to be at 0 and at pi, at those two different spots. So 0 degrees and at pi. Now, we could write that as 0 plus 2 pi n and pi plus 2 pi n. But we can condense both of those answers and write them just as pi n. Pi n will include all of these answers, because if I put 0 in for n, I get 0 degrees. If I put 1 in for n, I'm over here at pi. I put 2 in for n, I'm at 2 pi. And it keeps going around and hits every single 0 and pi and 2 pi and 3 pi, and it keeps increasing. So this would be the solution. So when you have solutions that are going to be pi away, a distance of pi, more than one solution, and pi away, then the general form usually can be condensed, or can be condensed. The same thing could occur if you have 4 angles that are all in these quadrants, like the 45s, where these angles here are pi halves away. Then I can write all 4 of those using plus pi halves, the first one plus pi halves. And so that happens within a unit circle sometimes when we condense their solutions. For this one here, we have cosine function. Now this one, I can't just factor out a cosine because we have this plus 2 here, but I see cosine squared, then a cosine x, then a number. So I'm thinking it looks like a trinomial, where I can factor it as I normally would for trinomials. So this would be cosine x and cosine x. And then to get 2 here and -5, well, wait a minute, I can't do that. This does not work. I cannot physically put that -5 there, so that will not work. So then I have to use other techniques to solve it, like the quadratic formula. So in this function, we have an a value that's 1, just 1 cosine squared x, a b value that is -5, and a c value that is 2. Those are from the function up here. So I plug those into the quadratic formula. It's not just x equals, now it's going to be cosine x is equal to opposite b plus or minus the square root of b squared, which is 25, minus 4 times a, which is 1, times c, which is 2, all over double a.
Yeah, I have superpowers.
You have superpowers?
Yeah.
Why do you have superpowers?
I've got doggy powers.
You have doggy powers?
Yeah.
That is awesome. So cosine x would equal 5 plus or minus the square root of 25 minus 8, 17, all over 2. And then we have two options here. We have cosine of x equals 5 plus the square root of 17 over 2, or we have it equal to 5 minus the square root of 17 over 2. Now, square root of 17, that's going to be between 4 and 5, closer to 4. We have to have this be between -1 and 1. So if we do 5 plus, like a 4, it's going to be 9, and 9 divided by 2 is greater than 1. So this one right here is not possible. If we do 5 minus 4, I get 1 and 1/2. So this one's probably possible, so we can actually plug that in, and we'll find x is going to equal the inverse cosine of, and I'm going to plug this into the calculator. So if I punch this in, I find an angle of 63.995. So I'm going to round that to about 64 degrees. So now, is there another spot within 1 unit circle? Yes, it'd be here and then down here, but the interval is between 0 and pi, so then this is the only answer I'd want. We also have tangent function we can solve, and we solve it similarly, how we have to first isolate the function. So here, tangent squared x would equal, subtract 2 to both sides, then divide by 9, so you get 1/9, and then square root both sides, So tangent x is going to be plus or minus 1/3. Now, I don't know where the tangent's 1/3 at. So I can plug this in the calculator and do like x equals the inverse tangent of 1/3. And I don't need to do positive, negative. I only need to do the positive one and use it as a reference signal. If I do that, though, I get a value 18.4, or approximately 18.4 degrees. And so then I know that this angle right here is going to be about 18.4 degrees. I know tangent is also positive in the third quadrant, so this would be the reference angle. It's 18.4 degrees. And so if I do 180 plus that, so I'm at 198.4 degrees. I can also, though, have positive or negative, plus or minus. So I need the other two quadrants. So I can do 180 minus this 18.43 degrees, and that's going to be 161.6 degrees. And then we can do a fourth one right here. This is 18.4 degrees. So 360 minus the 18.4, the 341.6 degrees. So these would be the four angles within 1 unit circle that would work for this. So another example here, let's isolate tangent again. So we have tangent squared x, or negative tangent squared x. Let's first subtract 3, then divide by the negative, which makes that tangent positive. And then we can square root that. So tangent of x equals plus or minus root 3. Now this is one we can actually look at and see on a unit circle. You should start to get comfortable with our 30, 60, 90 triangles. That's where we have the tangent being root 3 over 3, or just root 3. And here at 6 degrees, I know my tangent is going to be root 3. If you don't know it yet, you can go through that work of saying it's the y value divided by the x value, which will be multiplied by the reciprocal. So those reduce out, so I get root 3. So this point here does give me the tangent of root 3. But that's a positive, which also occurs down here. But then we also have the negatives in the second quadrant and the fourth quadrant are also possible solutions. And so our values are going to be the pi thirds plus, and actually we only want 1 unit circle, so I don't need the plus 2 pi m. Do 2 pi thirds, 4 pi thirds, and 5 pi thirds. Those would be the 4 angles within 1 unit circle. If I didn't have the interval here, I could write that as like pi thirds plus pi n and 2 pi thirds plus pi n. So I could write those 4 solutions using 2 different general forms for all possible solutions. So this is just one last example I want to talk about, is that sometimes they're hard to solve algebraically. So what we can actually do is graph both of them and figure out where their intersection points are to figure out the equivalency in them. So it'd be pi halves, and pi would be the 2 spots where these intersect. So I'm going to call that good for the examples for 14.4, and have a good night.